In this lesson, we want to talk about trigonometric functions of acute angles, and also we'll look at cofunction identities. So previously, we used angles in standard position to define the 6 trigonometric functions. So what we're going to do in this lesson is we're going to define our 6 trigonometric functions as ratios of the lengths of the sides of right triangles. So we're going to kick things off by looking at an acute angle in standard position. This is something we've already seen. So we've seen this diagram before. So this acute angle here, this angle theta, is in standard position, okay? And we've just picked a point on the terminal side. We're going to call it x comma y. That's our point. But again, this has actual coordinates. In this case, it would be 8 comma 8, okay? But we're just going to refer to it as x comma y. Now, generically, we know that this distance from here to here can be represented by just saying the letter y, okay? Because this right here is y, and down here, this coordinate is going to be 0, right? Because we're on the x-axis. So I could take y and subtract away 0, and I would get y. So that's my distance for this vertical leg here of this right triangle that we formed. Then this horizontal distance from here to here, remember this is a coordinate of x, okay? This is a coordinate of x, and this is a coordinate of 0, so really I could do x minus 0, and just say that the distance from there to there, we could say this is x, okay? And then from here to here, let me highlight this. From here to here, we know that is the hypotenuse, right? So we call this r. We call this r, and we'll get more into that as we progress through the course in terms of why we call it r. For right now, we just call it r, okay? So we've already defined the 6 trigonometric functions using these letters, right? So we've said that the sine of theta is y over r. We've said that the cosine of theta is x over r. We've said that the tangent of theta is y over x. And then using the reciprocal identities, we can get the 3 remaining ones. So the cosecant of theta is going to be the reciprocal of this, which is r over y. And keep in mind, if your denominator ends up being 0, okay, it's undefined. So I'm not going to write that, but y can't be 0 there. Then here you would have the secant of theta, okay, and this would be r over x. And then lastly, you'd have your cotangent of theta, which is going to be x over y. Okay, so let's explore a different way to look at this now. So instead of calling this guy y, okay, we're going to refer to it as opposite because it's opposite of this angle here, okay? Now, what you want to pay attention to is where this guy is, because in this case, this is the opposite side. But if I change the angle up, if I was measuring this angle here, well, then the opposite side would now be here. So you got to pay close attention to this. I'll show you some examples where we switch things up and the answers are going to change. So you got to keep in mind where the opposite side is. So this guy is opposite of your angle theta. And then this guy right here is adjacent to it. Okay, and then of course the hypotenuse stays the same. The hypotenuse is always opposite of your right angle, your 90-degree angle. Okay, so what we can do now is say that, okay, since this was y and this was x before and this was r, well, if we have sine of theta, okay, we said before this was y over r. Now we're going to say it's what? Well, y is the opposite, so I'm going to put OPP for opposite, and this again is the measure of that, so the length that you're given. And then you have your r, your hypotenuse. So I'm going to put HYP for hypotenuse. So opposite over hypotenuse, okay? And I'll give you a mnemonic device for this in just a moment, the SOH-CAH-TOA. So then you have your cosine of theta, okay? This is x over r, or in terms of this, it's the adjacent, okay? The adjacent over the hypotenuse, okay? And then you have your tangent of theta, which is going to be what? It's y over x, which is your opposite, okay, your opposite over your adjacent, And then, of course, you can flip these guys, and you can get your cosecant of theta. So your cosecant of theta, and I'm going to run out of room here. So let me actually copy this real quick. And let's go to a fresh sheet and just paste this in. So we have more room. So then I can say that cosecant of theta, which is the reciprocal of this, is going to be the hypotenuse over the opposite. And then your secant of theta, which is the reciprocal of this, would be your hypotenuse over your adjacent. And then lastly, your cotangent of theta is going to be the adjacent over your opposite. Okay, so how do we remember this? Well, recall when you work with something like the order of operations, you have your PEMDAS, right? Your please excuse my dear Aunt Sally. Well, you have a similar mnemonic device here. It's the SOH-CAH-TOA, okay? So the SOH-CAH-TOA, okay? So the S stands for sine, the C stands for cosine, and the T stands for tangent. Okay, so this is pretty much what everybody uses to remember these guys. So S for sine, it's the opposite over the hypotenuse. So opposite over hypotenuse. C for cosine, the adjacent over the hypotenuse. So adjacent over hypotenuse. The T for tangent, the opposite over adjacent. So opposite over adjacent. So this is something you want to write down and think about constantly until you have it memorized. It's going to save you a lot of time. And then, of course, if you know your reciprocal identities, it's very easy to get the cosecant, the secant, and the cotangent by just flipping guys. All right, so let's go ahead and take a look at an example. So with this guy right here, we're just going to find the 6 trigonometric functions. So let me just write them out. We want sine of theta, cosine of theta, and let's just do tangent of theta for right now. We know we can get the other 3 by just flipping these guys, okay? So what is sine of theta? Again, let me go back to the SOH-CAH-TOA, okay? So sine of theta, it's y over r, but let's think about it in terms of this. We're going to say opposite, so opposite over hypotenuse, okay? Cosine of theta, we're going to do adjacent, adjacent over hypotenuse. And tangent of theta, we're going to do the opposite over the adjacent, okay? So what's the opposite here? What's the hypotenuse? What's the adjacent? So we know that across from the right angle, okay, which is the longest side of a right triangle, is your hypotenuse, okay? So this is the hypotenuse right here, okay? And if you're confused about these things when you first start, go ahead and take the time to label things, figure out where everything is. So this guy right here is adjacent. This is your angle here, theta, okay? And I made that terribly. So this is your angle here, theta. This guy is adjacent to this, okay, or next to it. So this is going to be your adjacent. And then opposite of this, you're going to have this guy right here. So this is your opposite. Once you've figured this out, you're just plugging things in and you're done, okay? That's all you need to do. So what is the opposite? It's 2. What is the hypotenuse? It's 2 times square root of 5. Well, of course, you want to rationalize the denominator there. Let me just kind of scooch this down a little bit so we have some room. So I'm going to multiply this by square root of 5 over square root of 5. The 2's are going to cancel. So I'm going to have the square root of 5 over square root of 5 times square root of 5 is 5. Okay, so that's my sine of theta. My cosine of theta is the adjacent, okay, which is 4, over the hypotenuse, which is 2 times square root of 5. The 4 and the 2 would cancel to 2 up there. So again, you're just going to multiply by the square root of 5 over the square root of 5. And what does that give me? Well, 2 times square root of 5, 2 times square root of 5 over square root of 5 times square root of 5 is 5. So the last one down here, we have the opposite over the adjacent. So the opposite is 2, the adjacent is 4, so this is 1/2. Now we can flip these guys again and figure out our other one. So let me erase this. All right, so for the cosecant of theta, remember, that's a reciprocal of this guy, the sine of theta, okay? So I'm going to use the one before we rationalize the denominator to make it easy. So 2 times square root of 5 over 2. I just took this guy right here, okay, and I flipped it. That's all I'm doing. You can flip this guy too, but then you have to rationalize the denominator again. It's just double work, okay? So we've already done that. So cancel this with this. You just get the square root of 5. Then the next one, we would have the secant of theta, okay? And that would give me what? The secant of theta would be the reciprocal of your cosine of theta. So again, take the one before we rationalize the denominator, and I'm just going to say this is the square root of 5 over 2, and nothing really else you can do with that. So lastly, I'm going to flip the tangent of theta, okay, to get the cotangent of theta. And so if I flip 1/2, I just get 2 over 1 or 2. All right, so let's look at another example. We're going to have the same right triangle, but now we're going to change the angle. So before, our theta was here, okay? So we were talking about in reference to that angle. Now the angle has changed, okay? So this is our angle now. And so this guy right here now is the adjacent, okay? So this is the adjacent, and this is still the hypotenuse. That is not going to change because it's always across from the 90-degree angle or the right angle. And now if you look opposite of this, this is going to be this side over here, okay? So we've got our adjacent, our hypotenuse, and our opposite. So our sine of theta, again, So, SOH. So, sine is opposite over hypotenuse. So what's the opposite? It's 4. What's the hypotenuse? It's 2 times the square root of 5. You do need to rationalize the denominator here. So let me cancel this with this and get a 2 here. Okay, so 2 over the square root of 5. So this is multiplying by the square root of 5 over the square root of 5. And you're going to get 2 times the square root of 5 over 5. Now I want you to notice something. Sine of theta here is the same as cosine of theta here. Okay, we're going to talk more about this in a moment, but I just want you to notice that. All right, so I can flip this guy to get my cosecant of theta. Okay, let's just do that now. And I'm going to start with it in this form, and I'm going to say this is the square root of 5 over 2. Okay, let's erase this. So the next one I want, and I'm just going to tighten this down so we kind of make that a little bit neater. So let's move this down a little bit. Okay, so the next one I'm going to do, is going to be my cosine of theta. Okay, my cosine of theta. Again, this is the CAH part of this. So cosine is adjacent over hypotenuse. So where is the adjacent? That's 2. What's the hypotenuse? It's 2 times the square root of 5. Before I rationalize the denominator, let's cancel this with this and put a 1 up here. So this is times the square root of 5 over the square root of 5. And this gives me the square root of 5 over 5. Okay. Now I want you to notice that the cosine of theta here, okay, with this angle up there, is the same as the sine of theta here, okay, with the angle here. Again, we'll talk more about this in a moment. So let me flip this guy right here before we rationalize the denominator. The secant of theta is going to be the square root of 5, okay, over 1, but just square root of 5. So let's just kind of tighten this down a little bit so we don't have stuff all over the place. So let's move this down. And then lastly, we're going to have our tangent of theta and then our cotangent of theta. Okay, so what's the tangent of theta? That's the TOA part, right? So TOA, opposite over adjacent. So the opposite here, and I erased this, I apologize, this is the opposite here. Opposite is 4, adjacent is 2. So 4 over 2 or 2, okay? And if I flip this guy, remember, if you're flipping a non-fraction number or a whole number or integer, if you want to think about it that way, you just write the number over 1 and then flip it, right? So it would be 1/2. So this is 1/2. And again, if I look at the tangent of theta here, it's going to match the cotangent of theta here. So the tangent of theta here is 1/2, and the cotangent of theta here is 2. Those guys are flipped. So now the tangent of theta is 2, and the cotangent of theta is 1/2. So this is going to lead us to an important result. And we're going to talk now about something called cofunctions. So to talk about these cofunction identities, at least the first time you see them, it can be a little bit challenging to understand. So just stay with me for a moment. I'm going to show you when you get to the examples, they're very, very easy to figure out, okay? So even if you don't fully understand the concept, you can work the problems very, very easily. So the first thing is that we noticed that the sine of theta from the first example was equal to the cosine of theta from the second example. So I have the same triangle here. I've just marked it with different letters. There's no actual numbers here, okay? So we have this lowercase a, this lowercase b, and the lowercase c that's representing the lengths of the sides here, okay? So if we wanted, let's say we had this measure of angle A. So this is angle A. This is what we used in the first scenario. If we wanted sine of A here, okay? If we wanted sine of A, well, what is this going to be? Well, it's opposite over hypotenuse. Your opposite here is the lowercase a. Your hypotenuse here is lowercase c, okay? And then if you wanted the cosine, okay, of b now, okay, of b, so I'm changing the angle up. I'm here now. You're going to notice that's going to be the same thing. It's going to be a over c. And again, lowercase a, lowercase c. Because now this is your adjacent, okay, and this is still your hypotenuse. Remember, cosine is adjacent over hypotenuse. And you'll notice that, again, your sine of theta is the square root of 5 over 5. This is the first example where this is our angle. In the second example, the cosine of theta, here's our angle here, is square root of 5 over 5. So this relationship is always going to be true for the two acute angles of a right triangle. Okay, so since the sum of the three angles in any triangle is 180 degrees, and our angle C here, remember this is our right angle, it's exactly 90 degrees. So that means because the sum of all three angles is 180 degrees, the sum of the measures of angles B and A is going to be 90 degrees, right? These are complementary angles. We've talked about this before. If they sum to 90 degrees, two angles, they're complementary angles. So because these two angles, A and B, are complementary, and our sine of A is equal to our cosine of B, we say the functions sine and cosine are co-functions. We also say that tangent and cotangent are co-functions. And then we can say secant and cosecant are co-functions as well. And if you want to go back, if you look at the tangent of theta here, it's a half. And if you look at the cotangent of theta here, it's a half. Okay? If you look at the cosecant of theta here, it's square root of 5. And if you look at the secant of theta here, it's square root of 5. So how can we use this for practice problems? These are your cofunction identities. You just need to memorize them. It's something you're just going to plug into. So your sine of your angle A is equal to your cosine of 90 degrees minus your angle A. So for example, if it was sine of 50 degrees, well, you would just say this is equal to cosine of, let me make this a little bit better. So cosine of what? Well, you would say 90 degrees minus 50 degrees, that's 40 degrees, okay? And you can punch this up on a calculator and you see that those are the same. Same deal with cosine of A and sine of 90 degrees minus A, secant of A and cosecant of 90 degrees minus A, so on and so forth. You can copy these down. But basically, if we look at a problem like this, the cosine of 48 degrees, and we want to write it in terms of its cofunction, well, again, you just say, well, this is going to be equal to the sine of, you take 90 degrees minus the measure here, which is 48 degrees, okay? And what's 90 degrees minus 48 degrees? Well, it's going to be 42 degrees, okay? So we can say cosine of 48 degrees is equal to sine of 42 degrees, okay? So this number here and this number here, those guys, because these are, again, complementary angles, they have to add up to 90 degrees. So that's what you want to make sure of. And then make sure your cofunctions there. So cosine and sine, tangent and cosangent, secant and cosecant, so on and so forth. Let's do another one. So we have the tangent of 11 degrees. So again, I would do cotangent, okay, of 90 degrees minus 11 degrees. 90 minus 11 is going to be 79. So this would be cotangent, okay, of 79 degrees there. So the tangent of 11 degrees is equal to the cotangent of 79 degrees. Again, you want to check to make sure that this plus this is going to give you 90 degrees. Okay, so let's look at an example that involves solving equations using cofunction identities. For this guy right here, we're going to find one solution for the equation, okay? And we're going to assume all the angles involved are acute angles. So you'll see a problem like this or a few problems like this in this section. And solving it is very easy. Remember, I told you that this plus this, okay, is going to equal 90 degrees. So all I need to do is take the inside parts, the 2 times theta plus 20 degrees, and add this to the 3 times theta plus 5 degrees, and set this equal to 90 degrees, okay? I'm going to solve for theta, okay, my unknown angle measure. So what I'm going to do here is I'm going to combine like terms. So 20 degrees plus 5 degrees is 25 degrees. And 2 times theta plus 3 times theta would be 5 times theta. So 5 times theta plus 25 degrees is equal to 90 degrees. Okay, so just like I'm solving an equation, just like if I had x there, I want to isolate this guy. So I want this by itself. So how do I do that? I'm going to first subtract 25 degrees away from each side of the equation. So this is going to be gone. I'll have 5 times theta is equal to, what's 90 degrees minus 25 degrees? It's going to be 65 degrees, okay? So to wrap this up, what I'm going to do is divide both sides by 5 so that I can isolate theta. And I'll say that theta is equal to 65 divided by 5 is 13. And of course, you have degrees there for the units. So I would say theta is equal to 13 degrees. Now, if you want to check this, all you would do is plug in. So 2 times 13 degrees is 26 degrees. 26 degrees plus 20 degrees is 46 degrees. So sine of 46 degrees is equal to cosine of what? 3 times 13 degrees is 39 degrees. 39 degrees plus 5 degrees is 44 degrees. So is this true? Yes, it is, right? Sine of 46 degrees is equal to cosine of 44 degrees. Again, this plus this has got to be 90 degrees. And of course, you have your sine and cosine. In this lesson, we want to talk about trigonometric functions of non-acute angles, and also we'll learn about reference angles. All right, so let's start off with a concept of a reference angle. This is something that's very important in trigonometry. So first, from the definition, we're going to say that every non-quadrantal angle in standard position will have a positive acute angle known as its reference angle. So when we talk about the reference angle for an angle theta, it's written as theta prime. So you'll see here we have this theta prime. Okay, so this is your reference angle notation. Now, when we talk about the reference angle for an angle theta, then basically this is the positive acute angle that is made by the terminal side of our angle theta and the x-axis. So I'm going to go through this in each quadrant. In every case, I'm going to be thinking about an angle theta that is between 0 degrees and 360 degrees. If you get something that's outside of that, you're just going to find the coterminal angle that's between 0 degrees and 360 degrees, and you'll apply the little formulas that we're going to look at here. So what I'm going to start with is an angle in quadrant 1. So if I think about the positive acute angle that is made from the terminal side of this angle theta in the x-axis, well, easily I can see that theta here is going to exactly be equal to theta prime. So if you're in quadrant 1, then you can say that theta is equal to theta prime. So your angle theta is going to be its own reference angle. If you're in quadrant 2, you have to do a little bit more thinking. So now I'm thinking about this angle right here. Okay, so this is my theta prime. Let me use a different color that's going to show up here. So this is from the terminal side of this angle theta to the x-axis. So I'm always thinking about going to the x-axis. So that angle has this measure of theta prime. So how do we get this? What I would think about is the fact that if I took this angle measure here, which is a straight angle, the measure is 180 degrees. So I'm going to say in quadrant 2, I'm going to start with that straight angle, which is 180 degrees. And I'm going to say that I need to subtract away the measure of the angle theta. Right? So I'm going to take this part away, right? That's what I'm going to subtract away, and that's going to leave me with my theta prime that I'm looking for. Let me get rid of all this so that's more clear. So I'm going to subtract away my angle theta, whatever it is, and let me slide this down here, and I'll say that theta prime, or your reference angle, is going to be equal to 180 degrees minus theta. Again, this is in quadrant 2. All right, if we're in quadrant 3, well, now we have to think about this guy right here. So this is your angle here. And I only want this part right here. So coming from the x-axis going down to that terminal side, that's going to be my theta prime here. So in this particular case, in quadrant 3, we are going to start with our angle theta. So let me say theta prime is equal to our angle theta, whatever it is. And we are going to subtract away this straight angle here. So this part right here, that's what we want to take out. And that's going to leave us with this amount of rotation right there. So I'm going to take away that straight angle, which is 180 degrees. So in quadrant 3, your theta prime, or your reference angle, is your theta minus your 180 degrees. All right, now let's take a look at an angle that's going to be in quadrant 4. So if we think about one full rotation, so this guy right here, that's going to be 360 degrees. So if I'm in quadrant 4, I would start with 360 degrees. And then to get this angle theta prime here, which is going to be this part right there, well, all I need to do is subtract out this angle here, theta, right? I'll be left with my theta prime. So let me actually slide this down just a little bit, and I'll say that theta prime is equal to 360 degrees minus my angle theta. Okay, so we have summarized everything, and basically, when you get to the examples, once you've gone through how it works, you can just use this little table. After you work enough examples of this or get deeper into trigonometry, this is something you're just going to have memorized, and you won't have to consult a table or draw a sketch or anything like that. So I'm going to start out with 330 degrees, and I want to find the reference angle. So I know that this is in quadrant 4. So I look through my little cheat sheet here, and in quadrant 4, again, my theta prime is equal to 360 degrees minus my angle theta. In this case, it's 330 degrees. And so this is just going to be 30 degrees for the reference angle. And again, you can always make a sketch if this is not clear for you. So this would be a 330 degree angle. And a lot of you can just think about that and see that I would need 30 more degrees to get back to the x-axis. So that's your reference angle there. But again, you can also do it where you think about one complete rotation is going to be 360 degrees. So 360 degrees. And then you subtract away the part that you're not going to want to measure. So that's your angle theta there. And in this case, that's your 330 degrees. And that leaves you with your reference angle, which is this part right here, which is 30 degrees, right? So let me put theta prime is equal to this. Okay, for the next one, we have negative 250 degrees. So as I mentioned earlier, if you're not between 0 degrees and 360 degrees, find the coterminal angle. Now, you could do it this way, and a lot of people do, but I think finding the coterminal angle first is just worthwhile because it's just going to make the process easier. You can just use this. So for negative 250 degrees, I would start by just adding 360 degrees to find my coterminal angle, and that's going to give me 110 degrees. So now I'm thinking about a theta of 110 degrees. That's going to be in quadrant 2. So in quadrant 2, your theta prime is equal to 180 degrees minus this 110 degrees, and that's going to give me 70 degrees. So again, if you want to look at a little sketch, we think about an angle with a measure of negative 250 degrees. We're going to show that with a clockwise rotation. So I'm going to start here and go this way. So that guy would be negative 250 degrees. But again, you just work with the coterminal angle, right? So that's a 110 degree angle, same initial side, same terminal side. And so let's get rid of this, and we'll just work with this guy. And again, you can think about this logically. If I start here and I rotate 110 degrees counterclockwise, well, then I need to go another 70 degrees to get to the x-axis, right? 110 degrees plus 70 degrees is going to be 180 degrees or form that straight angle. Again, the other way you could think about it is your theta prime here is going to be your straight angle, which is 180 degrees, minus the part of this rotation that you don't want. So that's this part right here, which is your 110 degree angle. And so that's 70 degrees. Okay, so that's your theta prime or your reference angle. All right, let's look at one more. So now we have 560 degrees. And again, I would find the coterminal angle that's between 0 degrees and 360 degrees. So 560 degrees, let's say minus 360 degrees. And that's going to give me exactly 200 degrees. So this angle right here is going to be in quadrant 3. So in quadrant 3, we would say theta prime is going to be theta, which is 200 degrees, minus 180 degrees. So my reference angle theta prime is 20 degrees. So coming to our little sketch, again, if you wanted to think about it as a 560 degree angle, that's one complete rotation, which is 360 degrees, and then another 200 degrees to get to that point right there. But I just like to work with the coterminal angle. I think it's much easier. In this particular case, you think about the entire rotation here. So let me put theta prime is equal to, that's going to be 200 degrees. And then you want to subtract out the part that you don't want. Again, I'm thinking about from here, the x-axis to here. So that's going to be me taking out this straight angle here, which is going to be 180 degrees. So that gives me my reference angle, or this rotation from here to here, of 20 degrees. All right, so now what we're going to do is talk about trigonometric function values of special angles. So we have these 30 degrees, 45 degrees, and 60 degrees in terms of the angles that we're going to want to memorize the sine, cosine, and tangent values for, and then also your reciprocal functions. So your cosecant, your secant, and your cotangent. So I'm going to start off with a triangle that you should know from geometry. If you haven't taken geometry before, it's not that big of a deal. So this triangle is known as a 30 degree, 60 degree, 90 degree triangle. So this is a special right triangle. And so the side that's opposite of the 30 degree angle has length 1. The side that is adjacent to this 30 degree angle has length square root of 3. And then the hypotenuse here has length 2. So if I wanted to figure out the sine of 30 degrees, and then the cosine of 30 degrees, and then the tangent of 30 degrees, let's go ahead and set those up. So for the sine of 30 degrees, let me make this S a little bit better. Again, it's opposite over hypotenuse. So the opposite side here has length 1, and the hypotenuse has length 2. So this is 1/2. Then for the cosine of 30 degrees, it's going to be adjacent, which is square root of 3, over hypotenuse, which is 2. Now for the tangent of 30 degrees, it's going to be opposite, which is 1, over your adjacent, which is square root of 3. And of course, we would rationalize the denominator there, so multiply by the square root of 3 over the square root of 3. So this is the square root of 3 over 3. So square root of 3 over 3. Now, you could find your reciprocal functions if you wanted to. So you could take the reciprocal of this to get your cosecant of 30 degrees. You could take the reciprocal of this to get your secant of 30 degrees. And you could take the reciprocal of this to get your cotangent of 30 degrees. I'm not going to waste time doing that. I'm going to give you a table where everything's presented. I'm just showing you where this stuff is coming from. I'm going to do the 60 degree angle as well. So let me go sine of 60 degrees. And we know from a previous lesson that that should be equal to the cosine of 30 degrees. So this should be the square root of 3 over 2. And if we check that, well, if I look at this 60-degree angle here, well, the opposite is now going to be the square root of 3, and the hypotenuse is still 2. So square root of 3 over 2. So that checks out. Then the cosine of 60 degrees, again, we know that should be the sine of 30 degrees, so this should be 1/2. So if I look at my cosine of 60 degrees, it's the adjacent, which is 1, over the hypotenuse, which is 2, so I do get 1/2. Then for my tangent of 60 degrees, this is going to be equal to what? Well, again, I would just think about my opposite, which is square root of 3, over my adjacent, which is 1. So square root of 3 over 1 is just going to be the square root of 3. So the other angle that we didn't do was the 45-degree angle. So this is an isosceles triangle. It's the 45-degree, 45-degree, 90-degree. That's a special right triangle from geometry. Again, if you've never seen this before, it's not that big of a deal. I'm just showing you where the things come from. So if I want to write out the sine of 45 degrees, the cosine of 45 degrees, and then the tangent of 45 degrees. So for these two, it's going to be the same. Because let's say I start with this guy right here. Well, it's going to be the same as if I worked with this guy right here. It doesn't matter. They're both 45-degree angles. So if I take this one right here and I say opposite over hypotenuse, it's going to be 1 over the square root of 2. And if I rationalize the denominator, I multiply by the square root of 2 over the square root of 2. So this is the square root of 2 over 2. So this is the square root of 2 over 2. Now, let's say I start here and I say, what's the cosine of 45 degrees? Well, now it's going to be adjacent, which is 1, over your hypotenuse, which is square root of 2. Well, I just did that. So if I rationalize the denominator, it's square root of 2 over 2. And it wouldn't have mattered if I would have used this angle here. I would get the same result, okay? Now, the tangent of 45 degrees, you're going to think about your opposite. So let's use this one. So the opposite is 1. And then over your adjacent, which is 1. And again, if you pick this one, well, now the opposite is 1 and your adjacent is 1. So it does not matter. It's 1 over 1, which is 1. All right, so what I've done here is actually summarized all the information into a nice little table. So we already know where this information comes from. We looked at the sine, cosine, and tangent for 30 degrees, 45 degrees, and 60 degrees. For this table over here where we have the cotangent, the secant, and the cosecant for 30 degrees, 45 degrees, and 60 degrees, it's just found using the reciprocal identities. This is something you definitely want to commit to memory. These angles are going to come up over and over and over again, so it's just going to make your life a lot easier. Now, there's something you can search for called the hand trick if you want an easy way of memorizing this. All right, now let's talk about how to find the trigonometric function values when you have a non-acute angle, but your reference angle is still going to be 30 degrees, 45 degrees, or 60 degrees. So we're going to be able to use that table that we just looked at. So I'm going to start with this special right triangle that we looked at earlier. I've just flipped it around such that you can draw this if you want to. It'll make it easier to understand when I put this on the coordinate plane. So this is your 30-degree angle. I just want you to remember that the side opposite of this has length 1. And then your side adjacent to this is going to have length square root of 3. And then your hypotenuse, that length is 2. So what I did here was slap this on the coordinate plane. So you see that this point right here is the origin. And you see that this point right here, we're going to find the x value and the y value. And we'll talk about that in a second. But again, if you wanted to find the sine of this angle, which is 150 degrees, well, basically you would just find that point on the terminal side. And remember, you have sine of 150 degrees is equal to y over r, right? Sine of theta is y over r. Let me write out cosine also. So cosine of 150 degrees is x over r. And then we have tangent of 150 degrees. This is y over x. So we'll look at this in a moment and we'll compare it. Now, I want you to notice that you have this reference angle here, which is 30 degrees, right? Again, if you're in quadrant 2, you have this entire guy here, which is a straight angle, that's 180 degrees, and you subtract away the part that you don't want to measure, so that's 150 degrees. So 180 degrees minus 150 degrees is your 30 degrees. So that's the amount of the rotation left to get from the terminal side to your x-axis. Okay, so I want you to think about what would the x value be, what would the y value be, and what would the r value be. So the r value is simple, it's just going to be 2. So r is equal to 2. For your y value, again, opposite of the 30-degree angle, this side has length 1. So if I'm starting here and going here, well, I've traveled 1 unit up, and again, you see the 1 right there, so the y value here is going to be 1. When we think about the x value, notice that we're going left, right? If we go to the left of the origin on the coordinate plane, the x values are negative. So this length right here, we know that side adjacent to 30 degrees is length square root of 3. But again, because we're on the coordinate plane, this is the negative of the square root of 3 for this x coordinate right there. So let's put this right here. So the negative of the square root of 3 like that. Okay, so let me actually write this all out. So the x value here is the negative of the square root of 3. The y value here is 1, and the r value here is 2. We're going to think about these values here, and then we're going to compare them to these trig function values for this reference angle, which again is 30 degrees. So we have y over r. So y is 1 and r is 2. Then here we have x over r. So x is the negative of the square root of 3 over r, which is 2. And then here we have y over x. So y is 1 and x is the negative of the square root of 3. So let me actually rationalize the denominator here. So times the square root of 3 over the square root of 3. So this would be the negative of the square root of 3 over 3. Now I want you to think about these function values that we talked about. With a 30-degree angle, the sine of theta is a half, the cosine of theta is square root of 3 over 2, and the tangent of theta is square root of 3 over 3. So coming back here, you'll see that everything matches in terms of absolute value. Okay, so this leads to an important result. What's going to happen is if you want to find something in quadrants 2, 3, or 4, you just first find the reference angle. Okay, so if it's a reference angle of 30 degrees, 45 degrees, or 60 degrees, you can use your little table. We'll talk about other values later on, but for right now, that's what we're going to work with. So that's your first step. So you would figure out, in this case, what is the sine of 30 degrees? Then you would apply the appropriate sign based on your sine rules, right? So we know in quadrants 1 and 2, sine is positive. So here, the sine of 150 degrees is a half, because again, the sine of 30 degrees is a half, and it's going to be positive in quadrant 2, so you don't have to make a sign change there. But in quadrant 2, cosine is negative, right? So that's why the cosine of 30 degrees, which was the square root of 3 over 2, is not going to exactly match the cosine of 150 degrees. You have to apply that negative there to account for the fact that cosine is negative in quadrant 2, because in this case, your x values are to the left of the origin, and so they're going to be negative. Then when we think about the tangent of 150 degrees, again, in quadrant 2, you're going to be negative for your tangent value, so you have to take your tangent of 30 degrees, which is square root of 3 over 3, and then slap the negative on there to get your answer here. So let's go ahead and take a look at some examples. All right, so we're going to start out with cosine of negative 600 degrees. So again, I'm going to first find the coterminal angle between 0 degrees and 360 degrees, just to make my life easier. So let me put negative 600 degrees. I'm going to need to add 720 degrees to that. So that's going to give me 120 degrees. So this is what I'm going to work with. So the first thing is, if I have a 120 degree angle, my theta prime, which is my reference angle, is going to be, again, I'm in quadrant 2, so 180 degrees minus 120 degrees, which is 60 degrees. So this is my reference angle. Let me write theta prime is equal to 60 degrees, and we can erase this scratch work. Cosine of negative 600 degrees is equal to the cosine of this 120 degrees. Now, here's where you have to apply a little bit of thinking, and you want to say, well, this is in quadrant 2. Is cosine positive or negative? It's negative in quadrants 2 and 3. So I'm going to put equals here, and then I'm going to put the negative of the cosine of this reference angle, which is 60 degrees. Remember, when you talk about things in quadrant 1, so the 30 degrees, the 45 degrees, or the 60 degrees, everything is positive, right? All students take calculus. In quadrant 1, they're all positive. So that's why you have to apply this negative here to this result. So the cosine of 60 degrees, if you go back to your table, is going to be 1/2. So what we'll do is say this is equal to the negative of, again, the cosine of 60 degrees is a half. So your answer here for the cosine of negative 600 degrees is going to be negative 1/2. Okay, let's look at one more. So here we have the secant of 495 degrees. So again, I would first find my coterminal angle. So 495 degrees. Let's subtract away 360 degrees. And that's going to give me 135 degrees. So when I think about a 135 degree angle, again, I'm going to be in quadrant 2. In my reference angle, my theta prime is 180 degrees minus 135 degrees, which is 45 degrees. Okay, so that's what I'm working with there. So let me get rid of this, and I'll just state that the secant of this 495 degree angle is equal to the secant of this coterminal angle, which is 135 degrees. So this is equal to, if I'm in quadrant 2, secant is going to be negative, right? Remember, secant is the reciprocal of cosine. They're both going to be negative in quadrants 2 and 3. So I'm going to put this negative out in front to account for that. And then I'm just going to think about the secant of 45 degrees. So coming up to my table, if I want the secant of 45 degrees, it's going to be the square root of 2. So I'll say this is equal to, don't forget your negative, so the negative of the square root of 2. In this lesson, we want to talk about finding trigonometric function values using a calculator. We'll also discuss using inverse trigonometric functions to find angles. Okay, so the first topic here is going to be very, very simple. I just want to make sure everybody's on the same page with using their calculator. If you're using an online calculator, you can pretty much just skip this part of the lesson. If you see something like the cosine of 60 degrees, we already know from this special right triangle where we have 30 degrees, 60 degrees, and 90 degrees, if we want the cosine of 60 degrees, well, it's adjacent, which is 1, over the hypotenuse, which is 2, right? As a decimal, this is 0.5. So what I want everybody to do is pull out their calculator that they're going to use for this course, and it should have a sine key, a cosine key, and a tangent key. You want to figure out what mode you're in first. So most calculators have a radian mode. We're going to talk about radians later on. In a degree mode, you want to select degree mode. So you should be able to just hit the cosine key on your calculator. So it would look like that. And then basically you would have some parentheses that would open up, and you just want to type in 60. Don't worry about trying to find the degree symbol. If you're in degree mode, then it knows you're working with 60 degrees. So you hit the enter key after that. So you hit your enter key after that, and you should get a result of 0.5. If you're not getting 0.5, then either you typed in the 60 wrong or you're in radian mode. So it's very important, if you're not getting the right answer, to investigate and figure out what's going on. A common thing that books will tell you to do is always, before you start working, hit sine of 90 degrees in your calculator. So that's going to look like this. You're going to hit the sine key, and then you're going to put 90 inside of the parentheses. And again, you're just going to hit enter. And then that should produce a value of 1. If you get a value that's something like 0.894, you know you're in radian mode and you need to switch it. All right, so what we're going to do is just run through a few basic problems. Again, just making sure you're on the same page with me. So we have the sine of 170 degrees. So I would just hit my sine key. And then in the parentheses, type in 170. And then you're going to hit your enter key. And this should give you, let's say, approximately 0.1736481777. That's where my calculator cuts off. Usually the book will tell you where they want you to round to. So let's just say we want to round to the nearest 10,000th. So that's 4 decimal places. So 1, 2, 3, 4. Remember, this is the tenths, the hundredths, the thousandths, and this is the 10,000ths. So if I think about it, the digit that follows is a 4. So the 6 would be unchanged, and you could just get rid of all these digits that follow. So the sine of 170 degrees is going to be approximately 0.1736. All right, let's take a look at another example. So here we have the secant of negative 620 degrees. Now there's a few things here. First off, you might not have a secant key on your calculator. The calculator I use does not have a secant key. So you would say the secant of some angle theta, again, using your reciprocal identity, you could say this is 1 over the cosine of theta, since most calculators do have a cosine key. So you can convert this over and say this is 1 over the cosine of this negative 620 degrees. Now, another thing you might be concerned with, you've seen throughout the course, if I got a negative angle or an angle whose measure was greater than 360 degrees, I would always find the coterminal angle between 0 degrees and 360 degrees. Now, you could do that, but if you're using a calculator, you don't have to. This will automatically calculate the value for you. So you're just going to type 1, then the divided by key, hit your cosine key. When the parentheses come up, just type in negative 620. Again, don't worry about the degree symbol. Hit enter, and we're going to get approximately, let me just make a little border here. If I pick up my calculator, I'll say it's negative 5.75, and then I'm going to have 8770483. Now with this guy, again, if you wanted to round to the nearest 10,000th, that's pretty common for most books. Let's see, we have the tenths, the hundredths, the thousandths, and then the 10,000ths. So this is the digit that follows. So the 7 falls in the category of 5 or greater. So I would add 1 to this 7, and then I would cut all these off. So this will turn into an 8. So your answer here for the secant of negative 620 degrees is going to be approximately negative 5.7588. Okay, let's look at cotangent of 670 degrees. So again, you might not have a cotangent key, but more than likely you have a tangent key. So again, from the reciprocal identities, the cotangent of theta is equal to 1 over the tangent of theta. So really, you could just say this is equal to 1 over the tangent of your 670 degrees, like this. And again, you could just follow those steps with your calculator, hit 1, hit divided by, hit your tangent key, inside the parentheses type in 670, and then close the parentheses and hit enter. And so this is going to be approximately, let's say negative, I'm going to go 0.839099, and then we'll have 6312. And again, if you wanted to round to the nearest 10,000th, again, forget about the fact that it's negative. I know that throws off a lot of people. You've got 1, 2, 3, 4 decimal places. So this guy right here, the digit that follows is a 9. So add 1 to this 0, that's going to be 1. And then you can cut all these digits off. So rounding this to the nearest 10,000th, you're going to have negative 0.8391. All right, let's spend a little bit of time now introducing the inverse trigonometric functions. So these are going to be a little bit confusing for right now. When we get further into the course, we're going to spend a lot of time developing the whole thought process behind how and why these guys are going to work. For right now, I just wanted to think about something simple. Let's say you had the sine of 30 degrees. And again, we have our special right triangle here, so we can immediately see that the opposite is 1 and the hypotenuse is 2. So we know this is 1/2. And again, you can type that into your calculator and verify you would get 0.5 or 1/2 as a decimal. Now, what if you typed into your calculator sine inverse? So it's going to look like that, or you might see arc sine. That's another way to denote it. But basically, if you took this part right here, or your answer from this, so let's say I put that in the parentheses, this is going to give you this angle measure back. So in other words, it's undoing what you did here. Here you took sine of your angle, which is 30 degrees, and you want to find the opposite over the hypotenuse. So that gave me 1/2. Here you have the inverse sine, and you're taking your opposite over your hypotenuse, and it's going to kick your angle measure, which is 30 degrees, back out to you. So in other words, you could say that you have sine of theta is the opposite over the hypotenuse. And in this case, you have the sine inverse, which is going to be you plugging in the opposite over the hypotenuse, and you're going to get your angle theta back. But there's a problem here, okay? And it's kind of a big problem, but again, we'll talk about this more later on in the course. If you typed in, let's say, sine of 390 degrees, so this is an angle that's coterminal with 30 degrees, it's going to be in the first quadrant, and it's going to have a reference angle of 30 degrees, well, you would get 0.5 or 1/2. Now, I just saw that if I did sine inverse of 1/2, I get 30 degrees. So I'm not getting my 390 degrees back that I'm looking for. So what's going on? Well, the problem is that sine is not a one-to-one function. We talked about this earlier in our pre-calculus course, where for a one-to-one function to exist, you have to have for each x value a given y value, and for each y value a given x value. So for each x, there's one y, and for each y, there's one x. Well, that's not going to be true with your sine function. So what happens is you have to restrict the domain in order to make it a one-to-one function, and that leads to the fact that if I plugged in 1/2 here, I'm only going to be able to get something in quadrant 1, so that's 30 degrees. If I needed to find something else, well, then I'm going to use the concept of a reference angle, and I'm going to think about where sine is positive. So in other words, I know that sine is going to be positive in quadrants 1 and 2. So really, anywhere in quadrants 1 or 2 where I would have a 30-degree reference angle, well, basically, my sine value is going to be 1/2. If I did sine of, let's say, 150 degrees, that has a 30-degree reference angle, so that's going to be 1/2. If I added 360 degrees to that, I would have 510 degrees. And if I did the sine of 510 degrees, I would also get 1/2, so on and so forth. So if you ever get a question, and we'll see them later on in the course, where it says something like the sine of theta is equal to 1/2, well, there's an infinite number of angle measures there, where if you take the sine value of it, you're going to get 1/2. So generally speaking, when you see these questions, especially in the first part of trigonometry, they're going to tell you that theta is going to be between 0 degrees and 90 degrees. So you're going to be in that first quadrant where 0 degrees and 90 degrees will be included. So let's look at a little example here. So we have sine of theta is equal to 4/5. And here theta is restricted, like I was just talking about, to be greater than or equal to 0 degrees and less than or equal to 90 degrees. Okay, so for this one, again, we would just use our inverse sine function. So sine inverse of this guy right here. So this 4/5. So it's like I'm plugging in the opposite over the hypotenuse, and I'm looking for my theta, and this is going to come from quadrant 1, so I'm going to be good to go in terms of this restriction here. So let's punch this into the calculator. So hit your inverse sine key, hit 4, and then divide it by 5, close your parentheses, and let me move this over, and I'll say theta is equal to this, and I'll say this is approximately. Let's write out what we have. So 53.1301, and then 0.235. So let's again round this to the nearest 10,000th. So you have tenths, hundredths, thousandths. This is the 10,000ths. So the digit that follows is a 0, so we can just cut all these off. And this is in terms of degrees. So our theta here is going to be about, or you can say approximately, 53.1301 degrees. And again, if you didn't have this restriction here, you could really say that theta could be any angle in either quadrant 1 or quadrant 2, where sine is positive, where the reference angle is equal to this guy right here, right? So there's an infinite number of solutions if you take this guy away, this restriction. All right, so similarly, we have the cosine of theta. This is equal to 2/7. So here, again, we're going to say that theta is greater than or equal to 0 degrees and less than or equal to 90 degrees. So since this is positive, if we use our inverse cosine function, we're going to get something in quadrant 1, so we'll be okay. So I'm going to say that I want my theta to be equal to the inverse cosine, and some people write that as arc cosine like this. And basically, you're just going to plug this in here, so this 2/7. And this is going to spit out my angle, my theta, that will be in quadrant 1. So let's hit our cosine inverse button. And then inside the parentheses, type 2 divided by 7, close your parentheses and hit enter. And this is approximately, let's go ahead and say, I'll just write out everything it gives me. So 73.3984504. That's where my calculator stops. If we want to go to the nearest 10,000th, we have the tenths, the hundredths, the thousandths, the 10,000ths. Well, this guy's a 5 here, so let me add 1 to this, and we'll make this into a 5, and then you can cut these off. And this is in terms of degrees. So we would say that our theta here is approximately 73.3985 degrees. Now again, if you did not have this restriction here, then theta could be any angle that's in either quadrant 1 or quadrant 4, that's where cosine is positive, that has this reference angle. In this lesson, we want to talk about solving right triangles and also look at some word problems that involve angles of elevation and also angles of depression. All right, so let's just jump in and look at our first example. When we talk about solving a right triangle, we're just trying to find all the missing angles and all the missing sides. So in this particular case, we have our triangle here. We're given one side that has a value of 14, and then we're given one angle with a value of 37 degrees. So I know the measure of angle A is 37 degrees. I know the measure of angle C, because it's a right angle, is 90 degrees. You can write that in there. And so if you wanted to figure out what the measure of this angle is, well, you know that the sum of the three angles is 180 degrees. So you could say that 180 degrees minus your 37 degrees plus 90 degrees. This guy right here would be the measure of your angle B. So let's go ahead and crank that out real quick. So 37 degrees plus 90 degrees is 127 degrees. And if I subtract 180 degrees minus 127 degrees, I get 53 degrees. So the measure of this angle here is going to be 53 degrees. Okay, so you can write it like this, or some people will say that the measure of your angle B is equal to 53 degrees like this. So whatever notation your teacher prefers, that's how you want to give it. So I'm just going to erase this so we have some room. All right, so now we want to find these missing sides. So we have this guy right here and this guy right here. Okay, so I always use the information given so that I can get a more accurate answer. In almost every case, you're going to have to round, okay? And just get with your teacher or your assignment to know what you need to round to. So for these guys, I'm going to round to the nearest tenth just to keep it really simple. I'm going to start with the fact that I was given this angle here, which is 37 degrees, okay? So I know that sine of 37 degrees is equal to what? It's opposite over hypotenuse, okay? So the opposite side here is this lowercase a. And the hypotenuse here is given as 14. Remember, the hypotenuse is always across from your right angle, okay? So this guy is going to be 14, okay? So how can we solve for this a here, okay, the lowercase a? We just multiply both sides by 14 to clear the denominator, okay? So we'd multiply by 14 over here and by 14 over here, and this guy cancels with this, okay? Same thing we've been doing forever. So what is 14 times sine of 37 degrees? Well, if you punch that up on your calculator, you're going to get about 8.4. Again, if we go to the nearest tenth. So this guy right here, I'm just going to say that a is approximately 8.4, okay? So it's approximately 8.4. And I'm just going to write in that it's 8.4 here. Again, we know this is an approximation. Okay, so what about this lowercase b here? What's that going to be? Again, when you work with these problems, try to use the information that you're given, because in some cases, you're going to have to approximate your angle, so you won't have this guy available to you as an exact measure. So I'm going to go with the 37 degrees that they gave me, and I want to think about how can I get this guy right here? So we would use cosine now, because the side here, which is lowercase b, this guy is the adjacent side, and this guy is the hypotenuse. So if I did cosine, okay, cosine of 37 degrees, well, now this is equal to, again, the adjacent over the hypotenuse. And the adjacent is what? It's going to be this lowercase b. And the hypotenuse is 14. Okay, so same deal. Very easy to solve this. Multiply both sides by 14. And what are we going to get? Well, we know that this would cancel with this. And 14 times the cosine of 37 degrees, again, if you're rounding to the nearest tenth, you're going to get about 11.2. Okay, so let's just say that b here, I'm going to put 11.2. Again, we know this is an approximation. It's not an exact value. So we're going to put that b is approximately 11.2. So we've solved this triangle. Okay, we have a value of 8.4 and a value of 11.2 for those two unknown sides. Again, those are approximations. You've got your 14, which was given. You've got this angle as 37 degrees, which was given. We know this is 90 degrees. That was given. And then this guy we figured out was 53 degrees. All right, so let's look at a different type of problem. Now we're solving a right triangle, but we're given two sides. So if we want to start out by finding, let's say, the measure of this angle A, so the measure of this angle A, what can we do? Well, we're given the adjacent side, okay? We're given the adjacent side. Let me just write that down. This is equal to 4. We're also given the hypotenuse. Remember, this is always across from the right angle. So we're also given the hypotenuse. This is 15.4 here. Okay, so what trigonometric ratio is the adjacent over the hypotenuse? It's cosine, right? The cosine function. So we can go ahead and say that cosine of this angle A is going to be equal to, we would have the adjacent, which is 4, over the hypotenuse, which is 15.4. Remember, we're not done here, okay? We need to solve for A, which is our angle measure. How can we do this? We talked about in the last lesson the fact that you could use the inverse of cosine, okay, to figure out what the measure of this angle was. In other words, I'm going to take my inverse cosine function, and I'm going to plug this guy in, okay, the ratio in. So 4 over 15.4. And what I'm going to get out of this is going to be a value that's a measure of my angle A. Okay, and it's going to be approximated. I'm going to do to the nearest tenth. So if you punch this up on a calculator and you round to the nearest tenth, you're going to get about 74.9. So let's just say this is about 74.9. Okay, and this is going to be in terms of degrees. So let me put that there. And let me just erase this. We don't need this anymore. I'm going to say that this is approximately 74.9. Okay, in here, I'm just going to label this and say this is 74.9 degrees. But again, this is an approximation. So let me put my degree symbol there. And then let me label this as 90 degrees. We already know that because of the right angle symbol. Now, what's going to be the measure of this? Again, this is just an approximation, but essentially we know that all three angles here would sum to 180 degrees, or the measure of angle A plus the measure of angle B would sum to 90 degrees. So I could say the measure of my angle B here is approximately 90 degrees minus 74.9 degrees, which is 15.1 degrees. So let me go ahead and just write that in here as 15.1 degrees. Okay, so we have our three angles. Now what I want to do is I want to think about how I can find this guy right here. Okay, so the value of this lowercase a, the unknown side. So what I can do there is just use my Pythagorean theorem. We know that the length of one leg, which is 4 squared, plus the length of another leg, which is going to be a in this case, so that's going to be a, that guy squared, is equal to the length of the hypotenuse, which is 15.4 squared, okay? Now again, you're going to be estimating this. So 4 squared is 16, then plus a squared equals 15.4. If I square that, I'm going to get 237.16. So let me erase this. We're going to be solving for a. So I'm going to subtract 16 away from each side of the equation. Let me scroll down. I'll come back up. So minus 16 over here, minus 16 over here. This is going to cancel. So you're going to have your a squared is equal to, if I subtract away 16 over here, I get 221.16. Let me erase this. And let me just drag this up so we have enough room to work. Let's move this up here. And so what I want to do now is solve for a. Now, normally you would say a equals plus or minus the square root of this guy, right? But you don't need the minus here. You just need the principal square root. So a is going to equal the principal square root of 221.16. So that's approximately going to be 14.9, okay? Approximately going to be 14.9. So let me scroll back up, and we'll write this as our answer. I'm just going to put 14.9 here. So 14.9. And just to make sure everyone knows it's an approximation, I'll say a is approximately going to be 14.9. Okay. In some of these problems, you're going to have units. You might get inches or yards or feet or whatever you're working with. Just make sure you include your units. In this case, we're not given any. All right, let's look at a little word problem now. So when Max is 123 feet away from the base of the school's flagpole, the angle of elevation to the top of the flagpole is 26 degrees 40 minutes. We want to find the height of the flagpole if his eyes are 5.30 feet above the ground. So when you first see problems that involve the angle of elevation or the angle of depression, it's a little bit confusing. What you want to do to clarify things is always draw a little picture. Okay, so that's what I've done here. And so basically you can see that this part right here, remember his eyes are 5.30 feet above the ground. So 5.30 feet above the ground. So that's what this part is right here. If you think about this entire thing, okay, let me change the color here. This is what we're looking for. This height going all the way down. So it includes this 5.30 feet plus the measure of this side A. Okay, so we need both of those and we need to add them together. Okay, so what we're going to do is we're going to work on this part first. So how can I find this unknown side A? Well, I'm given this angle measure here, which is 26 degrees 40 minutes, okay? So if I know that I have this guy right here, which is the adjacent side, okay, and I want to find this part right here, which is the opposite side, well, what trigonometric ratio gives me opposite over adjacent? Well, I can use my tangent function, right? So I can say that the tangent of this 26 degrees 40 minutes is equal to the opposite side over my adjacent side, which is 123 feet, okay? I'm just going to put 123 just to work with the numbers for right now. Okay, so what we want to do is just multiply both sides by 123. And let me scroll down and get some room going. So I'm going to multiply this side by 123 and this side by 123. We know that this cancels with this, and I'm left with just a, okay? And it kind of looks like a 9, so let me make that more clear. So I would say that, I'm just going to flip this over and say a is equal to, or actually let's put approximately because we're going to have to estimate this. If I did 123 times the tangent of 26 degrees 40 minutes, I would get about 61.8 feet. So about 61.8 feet, okay? Now, and I could just put FT to abbreviate that. Now, if you're confused about how to enter this into your calculator, you have on a TI-83 or 84, whatever you're using, you can hit secant and then angle, okay? And you can choose degrees and you can choose minutes, okay? That way you don't have to convert it into a decimal and then type it in. It's a little bit easier and it'll be a little bit more accurate. All right, so A is approximately 61.8 feet. Now, we are not done. We haven't solved the problem yet. Let me erase all this and let's go back up. And let's say that This guy is 61.8 feet. But again, I'm trying to find the height of the flagpole, which goes all the way down, okay? Remember, his eyes are 5.3 feet above the ground, okay? So I've got to add these two guys together to get my final answer. So we're going to do 61.8 feet plus 5.3 feet, okay? And this would give me 67.1 feet.